What is nuclear fusion? Nuclear fusion is a reaction in which two or more atomic nuclei combine to form one or more different atomic nuclei and subatomic particles, neutrons or protons. The difference in mass between the reactants and products is manifested as either the release or absorption of energy. It's the opposite of the nuclear fission process used in today's nuclear power plants, which split atoms apart. The fusion of hydrogen nuclei into helium is the stellar nucleosynthesis that powers stars, including the Sun. Being able to create and harness the energy released from fusion reactions, such as the ones on the Sun, is the primary goal of an anthropogenic nuclear fusions, to produce usable fusion power.
The history behind nuclear fusion, 1920s to 1930s, understanding the stars and the atom. Robert Atkinson and Fritz Houtermans provided the first calculations of the rate of nuclear fusion in stars. At the same time, Ernest Rutherford was exploring the structure of the atom. With his famous 1934 experiment, Rutherford showed the fusion of deuterium into helium and observed that an enormous effect was produced during the process. His student Mark Oliphant used an updated version of the equipment firing deuterium rather than hydrogen and discovered helium-3 and tritium, showing that heavy hydrogen nuclei could be made to react with each other. This was the first direct demonstration of fusion in the lab. This understanding of nuclear fusion was tied together by Hans Bethes' work on stellar nucleosynthesis, where he described that it is through proton-proton chain reactions that the Sun and stars release energy. 1950s, enter the fusion machines. By the 1950s, researchers started looking at possibilities of replicating the process of nuclear fusion on Earth. And in 1950, Soviet scientists Andrei Sakharov and Igor Tamm produced the design for a type of magnetic confinement fusion device called the tokamak. This design was followed by, in 1951, by Lyman Spitzer's concept for the stellarator. The stellarator concept dominated fusion research throughout the 1950s, but lost its sway when the experimental research on tokamak systems by Soviet scientist Lev Artsemisov showed that the tokamak was a more efficient concept. 1980s to 2000s, jet record. The first experiments using tritium were carried out in JET, or the Joint European Torus, making it the first reactor in the world to run on the fuel of a 50-50 mix of tritium and deuterium. In 1997, using this fuel, JET set a world record for fusion output at 16 megawatts from an input of 24 megawatts of heating. This is also the world record for Q at 0.67. It should be stated that the world record was achieved in a very short instant of about 1 second. A Q of 1 is break even, and to achieve fusion energy the Q value must be greater than 1. The aim of ITER is to achieve a Q of 10. 2000s to present, a home for ITER. In 2005, the members of ITER, the world's largest and most advanced fusion experiment, unanimously agreed that ITER would be built in Cadarache in France. In December 2022, the ITER project passed the 77.7% milestone of work scope completed to first plasma. In 2015, the Weitelstein 7X stellarator, which is a long-term backup strategy for the tokamak in the European fusion roadmap, came into operation, and its first operational campaigns exceeded all expectations. In 2021, a new fusion energy world record of 59 megajoules was achieved in JET in a 5-second pulse, while burning only 170 micrograms of deuterium and tritium. ITER is currently being built in southern France with an international collaboration between China, Europe, India, Japan, Korea, Russia, and the United States.
How nuclear fusion creates energy. Nuclear fusion is a process that occurs when atomic nuclei come together and combine to form a heavier nucleus, releasing a tremendous amount of energy in the process. The fusion process is responsible for powering the stars, including our Sun, and scientists are actively working to harness this energy for practical use on Earth. In the context of controlled nuclear fusion, the most promising approach involves using a combination of hydrogen isotopes, deuterium and tritium, as fuel. These isotopes are heated to extremely high temperatures and placed under intense pressure to overcome the natural electrostatic repulsion between atomic nuclei and bring them closer enough together for fusion to occur. The fusion reaction between deuterium and tritium produces a helium nucleus and a high-energy neutron. This reaction releases an enormous amount of energy according to Albert Einstein's famous equation E equals mc squared, which states that mass can be converted into energy. In the fusion process, a small fraction of the mass of the hydrogen isotopes is converted into a significant amount of energy. The released energy primarily exists in the form of kinetic energy of the particles generated during fusion. These high-energy particles collide with the surrounding matter, heating it up. In a fusion reactor, the heat is transferred to a coolant, such as water or gas, which then goes through a heat exchanger. The heat exchanger extracts the thermal energy from the coolant and uses it to produce steam. The steam drives a turbine, which in turn drives a generator to produce electricity.
Its implications and what nuclear fusion can achieve. The outlook for nuclear fusion as a viable energy source is generally positive, with many scientists and researchers optimistic about its potential. However, it's important to note that predicting the exact timeline for when fusion power will become a practical reality is challenging. Estimates range from a few decades to the second half of the century. Achieving net energy gain and demonstrating the economic viability of fusion remain critical milestones. It's important to note that scientific breakthroughs or unexpected technological advancements could accelerate the timeline. Fusion offers several potential advantages. It utilizes isotopes of hydrogen, which are abundant and can be extracted from seawater, making the fuel supply virtually limitless. Fusion reactions do not produce long-lived radioactive waste as in fission reactions, reducing concerns about nuclear waste disposal. Fusion power could be inherently safe with no risk of meltdowns or catastrophic accidents. However, despite progress, several technical challenges remain. Sustaining a stable, controlled fusion reaction for a long duration, developing materials that can withstand the extreme conditions inside a fusion reactor, and finding efficient methods to extract and utilize the generated energy are among the ongoing areas of research. Overcoming these challenges is crucial to achieving practical fusion power. In summary, nuclear fusion holds great potential as a clean, safe, and virtually limitless energy source. While challenges persist, continued research, international collaboration, and the construction of large-scale experimental reactors such as ITER contribute to a positive outlook for fusion. With sustained efforts and further advancements, fusion power could become a significant part of our future energy mix.
Problems with it. While nuclear fusion holds great promise as a future energy source, there are several significant challenges and problems that need to be addressed. Here are some key issues associated with nuclear fusion. Energy input versus energy output. One of the primary goals of fusion research is achieving net energy gain, where the energy produced by the fusion reactions exceeds the energy required to sustain that reaction. So far, fusion experiments have not yet achieved this milestone, and achieving self-sustaining fusion reactions remains a major challenge. The energy input required to initiate and sustain fusion reactions, along with energy losses during the process, need to be minimized for fusion to be a viable energy source. Cost and economics. Building and operating a fusion power plant is expected to be a complex and expensive endeavor. The development of fusion technology requires substantial investment in research, infrastructure, and construction of large-scale reactors. The high cost of building and maintaining fusion reactors poses a significant economic challenge, and it is uncertain how long it would take to achieve a cost-competitive fusion energy system. Safety and environmental concerns. While fusion reactions themselves are considered inherently safe, there are other safety considerations. The high-energy neutrons produced during fusion can activate the reactor's structural materials, making them radioactive. Proper shielding and handling of the activated materials pose challenges for both operations and decommissioning of fusion reactors. Additionally, the large-scale deployment of fusion power plants will require addressing potential environmental impacts associated with the extraction and processing of fusion fuel. as well as waste management.